Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content.
Alright, great guys. What we're going to be doing today is a consolidation session. And I hope I've spelled that word right, because otherwise it's going to make me look extremely bad. Yes, I have spelled it right. Okay, fantastic. Okay. And what we're going to consolidate today is types of forces or forces. Okay, now of course this is a consolidation session. We've already recorded the formal lesson of this, so we're just going to try and go through the main points, of course, of this topic. Okay, now the types of forces that we get, of course, in big or main categories is we get contact forces, and then we also get field forces. Okay, now these can be further broken up, of course, into some more categories. Okay, so especially for contact, we've got 3. Whilst as for field, we have also 3 as well. So let's consolidate them quickly. For contact force, we've got force of compression. And then, of course, we've got friction and tension as well. Now, of course, friction, tension, you will be dealing with a lot in grade 10, 11, and 12 physics. Okay? I teach it every single time. Field forces, we have magnetic. Okay, magnetic force. Okay, hope we can all read that as magnetic. We have gravitational. Gravitational force, force of gravity, and then of course we have electrostatic. Okay, we're going to have a look at all of these in just a moment. Forces, we must understand, to think about forces, or to better understand it, you must realize that force exists all around us. Okay? We actually use force in everything that we do. Most common example of using a force would be to either push or pull a door open, right? Or even closed, okay? Some doors require a larger amount of force than most, especially the doors that don't have handles, or especially if the door is a little bit stuck, and then we need to obviously add some more force in there to get the door open, okay? But forces exist everywhere, and that's just a common everyday example. That's okay. But forces are also needed even when you are sleeping, believe it or not. There's even force that's needed there, okay? And that force, just off the top of my head, one of those forces, if there is more than one, but one that I definitely know off the top of my head, is the force that keeps you on the bed. All right? Otherwise, you'd be levitating or floating while you sleep. And that's like borderline horror movie type vibes. And I don't like horrors. Okay. But forces are needed even to start things. All right. They needed to also sometimes stop things. Forces are even needed to push or move rather your chest up and down for breathing. That is an actual force. Believe it or not. Okay. Sometimes forces are even needed to change direction. Right, even to change shape. And compression would be, for example, changing the shape. Okay, you can compress clay. Okay? You can compress it, or even a hold on, I have an example here, and I'll face reveal for this one. So just give me one moment. Okay, so my camera goes on. You'll be able to see me, and you'll see that I have a little obviously on the screen recorder you can't see it, but those in the live class will see it. That I've got a little stress ball. Okay, it's $5 at the crazy store. Okay, and obviously this, if I must press down, this is a compression force. Okay, it's the force of compression. Okay, which is obviously me just pushing down, and when I push down, obviously the round spherical ball that I would have had changes shape. Okay, I've manipulated the shape. Obviously it forms back there, but this is a compression force, even with 2 hands as well. It's compressing, which you can obviously use for dough as well. So that's still a type of force. Cool. So obviously compression would be an example of a contact force, as you saw my hand making contact with the stress ball. All right, or you can just picture that for those watching this. Okay, what is force measured in? Okay, force is measured in newtons. Okay, capital N, newtons, and the symbol, of course, is just a capital N, showing that that's what it is measured in. It was named after an English scientist called Sir Isaac Newton. Okay, and in grade 10, 11, and 12, obviously, they do give a little bit more history about Sir Isaac Newton. So no, they do not require you to know when he was born. They do not require you to know in what year. Okay, but I believe, if I must think about it off the top of my head, I think it might be 17th or 18th century. I don't want to guess. So I'm just going to leave that as an open research if you want to. You don't have to. Okay. Sweet. Ow, excuse me. Now, the next thing I need to mention about contact forces, because we're going to go and dive a little bit into this one first, okay? When two forces touch one another, they are in contact, okay? And that's why with compression, which we'll get in just a moment, okay, is a contact force because two forces are touching one another. The forces include a push and pull, all right? Okay, and when you got a push versus pull, or even, for example, a pull versus pull, okay, this can obviously make sense a little bit if you are playing the game tug of war. Sometimes in tug of war, you'll find that nobody moves, or the rope doesn't move, because usually there's a little thing in the middle like red tape, or maybe the two ropes are linked in the middle, and then of course now two teams, maybe a group of 5 maybe to 10 are pulling the rope. Okay, now obviously with tug of war it's two pull versus pull forces, okay, which creates a force known as tension. There's tension in the rope. Okay, there's tension in the rope. Okay, and often only a team can win if one of the teams pulls with a greater force, of course, than the other to overcome the other team's force. Okay, which would be tension. Okay, another example of tension would be a car towing another car with a rope in the middle. That's tension. Okay. Another example of a contact force would also be friction. I've already demonstrated compression when you're squeezing a stress ball or even a tennis ball, but friction, talking about friction between two objects, okay, could be an example of an eraser. An eraser erasing pencil, writing on a piece of paper. If you must erase extremely hard or extremely fast, like an entire page worth of pencil vibes, okay, then what you're going to find is that your eraser becomes a little bit warm, okay, because there's friction between the rubber or the eraser, okay, and the page itself, okay. That's called obviously a contact force, okay. Friction also exists, okay, when you are moving forward, because friction is the opposite of the forward force. Friction always pushes in the opposite direction. So when you are driving, okay, not when you're driving because that's illegal, but when your parents are driving or you're driving in a car, and sometimes you see that the car's tires make skid marks or tire markings on the road. That's a result of course, friction, because there is a force going in the opposite direction to the tires, or in the direction that the car is obviously moving. So contact forces are by far a bit easier to understand, as the content for them is not as big, of course. But a contact force generally consists either of a push or pull like motion. Push or pull type motion, or push or pull categories, even under within contact forces, or just in general. Okay, to change the object's state of motion from rest to motion, or from motion to rest. A better way to explain friction is that in the laws of force, because in grade 10 and 11, we go through, sorry, not grade 10, I think more specific in grade 11, we go through something called Newton's law. So let me just kind of give you guys a little push into the future without confusing you all too much. A sip of coffee first. Is that at the moment I'm standing in front of a wall in my room and I'm pushing against the wall right now. Now, one of Newton's laws says that for every action there's an equal opposite reaction. Okay, and in grade 11 there's a better way to even word that, but that's the most simplistic way. So at the moment I'm pushing against the wall with a particular force. But the reason why the wall is still standing is because the wall is pushing back against my hand, which in turn is pushing against my entire body with the same amount of force. Hence, the forces are now balancing each other. If that was not so, okay, if that was not so, I'd push straight through the wall. Straight through it. I'd fall straight through it because there's nothing holding or pushing against my body or my hand. Now, of course, we know the property of a wall is made up of solid concrete, solid brick. Of course, that's able to withstand a large amount of force. That's why no one can break down their house without using a 10-pound sledgehammer of some sort. And even that takes some time. It's meant to withstand a lot of force. Okay, so friction, in this case, with me pushing against the wall, or me even leaning against the wall, must lean against me with that same amount of force to cancel the phenomenon out. So I'm pushing back with a positive force, and the force is pushing against me in the opposite direction, so that's negative. So -2 plus 2 is 0. So in other words, the forces cancel and they're 0. Let's have a quick squiz at field forces. Now, field forces are also called non-contact force. And in fact, that these forces, they act at a distance between two bodies. Which obviously, as you can see there, the three categories: magnetic, gravitational, as well as electrostatic. Now, if we have a look at gravitational first, which is by far most relevant to us even currently right now. Okay? Because gravity will affect anybody. Gravity don't care who you are. Gravity don't care how light you are, how heavy you are. Everything happens equally under gravity. That's why we walk on the ground. Yippee! Okay? Now, gravity, of course, or gravitational force, is a force that pulls objects to the earth. Okay? That's why we walk on the ground, because we are being literally forcefully pulled, all right, towards the earth. Okay, so gravitational force would be an example. If we just want to look at the two categories of push and pull, it'll be a pull force. Okay, it's pulling us down. When you drop anything, of course, it falls to the ground. If you jump up, the ground pulls you back down, okay, to keep you humble. Okay, the bigger the difference in mass between two bodies, the bigger the force of attraction will be. So in other words, if you drop a feather, you'll see the feather takes its time to hit the ground. And also when it hits the ground, it doesn't really make a sound. If it does make a sound, it makes a sound for us that's too small for us to hear. However, if you drop a brick, right, or a building drops, it makes a loud thud. Okay, so the bigger the mass between two bodies, the bigger the force of attraction will be, because gravity, by the way, or gravitational force, is also a force of attraction, is an attractive force. Some things coming together, even from a distance. Okay, so it doesn't matter if I jump up, which is a small distance compared to me skydiving. Skydiving, it really doesn't matter. I'm still falling. Okay, the earth is still pulling me towards itself, no matter how high above it I am. But however, no contact is made until I obviously reach the earth. Okay, now force or weight.
Excuse me.
Sure.
Can can you please explain the difference between I think it's weight and mass? I'm not sure,
To
but
what?
my teacher explained it or something, and I just didn't understand it.
Sure, no problem, Jenny. You actually took the words out of my mouth. That's exactly what I was about to explain. So you are so spot on for that. Thank you. What I was about to say, exactly what the question that Jenna asked, was the difference between weight and mass, and why weight must not be confused with mass and vice versa. Okay, let's maybe just erase this section quickly. Okay, cool. Let's just go back to the pen. Okay, so let's talk about mass versus weight. Now, we often hear this word, or the first part here without the T, and also the part with the T, how much do you weigh, or your weight. In other words, I need to lose weight, or I need to gain weight, or something like that. No, that is actually the incorrect term that we use as human beings. Okay, and if you're a scientist or a science learner, the teaching is therefore fixed with you. Okay, you actually to gain mass. Okay, let's explain the obvious differences. Okay, so one, mass is measured in kilograms. Okay, it is measured in kilograms. Kgs. Okay, or just kg. Let's take the s away. Okay, kilograms. How many kilograms do you? How many kilograms do you? So obviously, it's obviously also scientifically incorrect to say how many kilograms do you weigh. Okay, because weight is measured in newtons. Okay, someone asks, what is your mass on the scale? Okay, I currently, according to the scale on Saturday, at about 2 or just before 2 o'clock, I weigh 103 kilograms. Okay, it's the most I've ever weighed in my entire life. Okay, thank God it's not all fat. Okay, so 103 kilograms is a mass, it's a scalar physical quantity. It's a physical quantity. Okay, so let's add that in there. It's a physical quantity. But weight, however, is measured in newtons. Okay, N. Okay, because it is a force. Okay, and the formula for weight, okay, is W is equal to mass times gravity. Okay, of course, where mass is equal to, or M is equal to mass in kilograms, and G is equal to 9,8 meters per second squared. Okay, which is obviously what gravity is equal to, the acceleration due to gravity. Okay, so their weight is going to be measured in newtons. Okay, your weight is going to be measured in newtons. So your weight is actually newtons. So if we must take an example, my 103 kilograms multiplied by 9,8, we'll find out what my weight is equal to. So I've actually never calculated this. Or the last time I did, I weighed like it was like 4 years ago, I weighed like 85. So 103 multiplied by 9,8. My weight is currently 1009,4 newtons. That is my weight. Okay. Now your mass, okay, will remain the same. Okay, no matter which planet you're on. Example, the moon has a gravity that is a gravitational force or gravitational acceleration that is less than Earth. Okay, it's way less than Earth. Okay, it's not at 9,8 meters per second. As you see over there, this is the value of gravity on Earth. Okay, let me just put this on here, on Earth. The moon is a bit less. Let's say the moon is about, they haven't really confirmed what is the gravity on the moon, but let's say the moon is about 6 meters per second, all right, or 6 meters per second square is the gravity on the moon. Your weight on the moon will be different because it's measured in newtons. Okay, so your mass, so my mass on the moon will stay 103 kilograms. Put a scale on the moon, I'll still weigh that, but the acceleration due to gravity on the moon is different. That's why people can hop and sort of semi-float in the moon or on the moon, because the gravity is different. Okay, so my weight will be in newtons. This will obviously decrease. Okay, so the main difference between mass and gravity is that your mass will be the same no matter where you are, but your weight can change depending on the value of gravity. Then the next type of non-contact force or field force that we get is a magnetic force. Okay, now we all know how a magnet looks. We've all seen a bar magnet, a normal bar magnet maybe before. If you have not seen a normal bar magnet before, I'll draw the opposite ends for you quickly. So let's just put a head in here, magnetic force. There we go. It's a normal bar magnet. There we go. Let's say this is the north pole of that magnet, and then of course going this way. Oopsie. The south pole. Okay, north and south pole. Okay, so what happens when opposite poles in a magnet meet each other? There'll be a force of attraction. Okay, so they will, the magnetic field lines will do something like this. Okay, and of course there'll be lines in the middle as well. They'll just keep going for each other. It's a force of attraction. However, if this S was another north pole, the field lines would converge. In other words, they'd go their own opposite ways. They wouldn't make contact. You cannot push together north and north or south and south pole, because the magnet will then not attract, okay, to each other. That's just magnet on magnet. However, there are certain substance or certain objects that are magnetic, such as metal. Metal's very, very magnetic. Okay, and probably the number one type of magnetic substance. Then you get a lot of stuff that are not magnetic, such as plastic. Plastic is non-magnetic. Okay, so all magnets, they do have two poles, north and south, as we can see there. Some objects that are not magnetic, they are classed as non-magnetic substances. Some metals are included here. So I mentioned plastic, another one would be wood, but metals that are non-magnetic are aluminium, brass, as well as copper. In other words, the magnet, you can put the metal on the magnet and there'll be no force. In other words, you'll be able to put it on, lift it up, put it up, lift it up, it'll be fine. Okay? Cannot magnetize it. It will not be magnetized at all. But good magnetic substances are, for example, iron. Iron is a very good example that of an object that is magnetic. It's a type of metal that works the best there. Okay. But the Earth is like a magnetic field, of course. Okay, the Earth is like a magnetic field. It can be looked at like a giant bar magnet. Okay. However, we know there's a North Pole and a South Pole on planet Earth, okay? And I mean, I don't know if any people haven't journeyed to, I mean, I've heard a lot about the South Pole, I'm not sure about the North Pole. That's why they made a story about Santa Claus there. But if the Earth is a little bit different, there is such a thing as true North and true South, okay? Which is basically the Earth's magnetic poles are realigned, or they are slightly off what we know as north and south. They are called true north and they are called true south. And in the previous lesson we had on forces, I did draw how that obviously looked. I did draw that. Okay. The last one is electrostatic force. Okay. Let's just get this one down. Ooh. Okay, now electrostatic force is dealt with a little bit differently in grade 11. Okay, grade 11, we take it further into, we take it a little bit further in the fact that there's two charged objects, and we try to find out what is the electrostatic force or between them. Okay, but in grade 9, of course, we still have a look at them in more layman's terms. Okay, now just to breeze through this quickly. In grade 8, we obviously learned that charges repel one another that are alike, and charges that are unlike obviously attract each other. So it's very similar to magnetic. Okay, so just like with magnets, unlike poles attract each other and like poles repel. The same thing with charges. Okay, so if you have a charge that like charges, I was going to write like instead of like. Like charges repel each other. So in other words, positive to positive. And unlike charges attract. So a negative and a positive force. Okay, now electrical charge, all right, they can either be positive or negative. Okay, now if we have a look at the work done by friction, okay, which you get to learn a little bit more in depth in grade 10 as well as 11 and 12. But if you take two objects together, like sometimes rubbing two objects next to each other can create a spark. It can create fire. Okay? But sometimes rubbing two objects together, like your ruler on your head, can create or develop charges. Okay? Now, the charges that developed, they can either gain electrons or they can be the loss of electrons. Okay. Only the negative electrons or the negative or electrons are negative, so only they can move. The positive protons don't move. Okay, so electrons are negative. Okay, they are negative and they can move. In other words, they can move from object to object. But obviously, if there's a bit of contact with those objects, of course. And protons, which are the positive charges, protons, can't move. Okay, because they are positive. Electrons, of course, they are negative. Okay, so sometimes, I don't know if you used to take off your jersey, but there used to be like sometimes crackling noises, particularly when the air is dry or something, or if you sometimes rub a plastic comb through your hair would sometimes stand, or taking your ruler and rubbing your taking a ruler and rubbing it quite hard or quite fast on your hair, and then you putting your ruler on your page, especially one of those shatterproof rulers, the page would be lifted or be attracted to the ruler for some time. Okay, for all those electrons were obviously transferred. Okay, these charged objects in an electrostatic system, they do possess potential energy. And that energy obviously comes from work done by friction. So the work done by you rubbing your ruler on your head, that's friction, of course. And your head even begins to feel a bit of heat from it. Okay? And if you rub it too hard and too fast, you might just get sore. Okay? But there's energy, obviously, for that work. Okay? Now talking about electrostatic force in real life. Okay? When thunderclouds develop, okay, a bit of geography coming here. I did draw this diagram before, but let's talk about it quickly. When thunderclouds develop, the air and the water particles, they rub against each other and they develop charges. And that's how we get lightning. Okay? Lightning is a very powerful discharge of static electricity. Okay? But I guarantee you, if it hits you, you will also become static. Is that you will not be able to move. Because 9 times out of 10, you will be dead. I know people that have survived being struck by lightning before, no doubt. I take my hat off to them. I've seen a video where a man was struck by lightning twice in the same spot. He was struck by lightning while running, laid there on the floor, realized he was still alive, tried to get up, lightning struck him again, and he was able to get up the second time. But he got up very slowly. Okay. So the spark can be more than 1 kilometer long. Now, a kilometer is 1,000 meters, so 1,000 meters worth of static electricity is hitting. Okay, hitting the earth and hitting objects in the earth. Sometimes when lightning strikes a tree will burn from the inside out. Okay, and as cool as that may look, obviously it kills the tree. Okay, and it's also very dangerous if there's a lot of trees that are burning internally. Okay, but it's still pretty cool. Okay, so that's an example of real life static electricity and real life electrostatic. Static electricity, electrostatic, whatever. Sometimes we hit static electricity, but when we touch a trolley at Pick and Pay, you know, the steel trolleys, the metal trolleys, of course. A doorknob, a metal doorknob, sometimes we touch it and we get that shock and we actually hear that sound of that electricity coming out. Really is quite sore at the time. It's a small amount of electricity, but it's enough to make you like be scared to touch a metal surface. Because this especially happens in dry conditions, very dry conditions, sometimes in very cold conditions as well. It'll just hit you like a ton of bricks. So I used to be very careful to touch metal chairs, or I used to use something else to move the chair or move it on the plastic area because I didn't want a shock from static electricity because that obviously can hurt. But again, just to make sure how thunder works, obviously there's an upward movement of water, of droplets and ice and whatever, and rubbing up against each other. And when those two different particles, which is water and air, rub up against each other, a spark forms in the form of lightning. And obviously lightning does obviously occur in storm situations. Okay, but those are all the types of forces that you learn under or in this grade, and that do exist and that we do take forward all the way through until grade 12 physics. Thank you so much for joining me, grade 9s. Please don't forget to like, comment and subscribe on all the videos that you see here on the Good Better Best channel, and we'll see each other next week.